So yeah, let's pick up where we left off here, and oops, I forgot to open up one small thing over here. We learned about linked lists, the data structure. It's got a bunch of nodes with, at each node we have data values of some type, could be ints, could be strings, doesn't matter. Something is there. And then there's always a next pointer to another node in the list, okay? And there is some pros and cons of using linked lists. They're like a competitor to arrays and vectors. There's the concept of going through them and like you're getting something out in an order. There's an order of all the data, and so it's very similar in that sense to arrays and vectors, but it's easier to like add stuff to the start, add stuff to the end, which is wonderful. So let's scroll down. So we're learning like what are the kinds of operations we want to have if we turned our list into like an ADT. What's the names of things we want to be able to do, like insert at the beginning, like push front, push back, get the size, see if it's empty, stuff like that. And so yeah, we got into that a little bit. And so we know that at each list, for each list, what we want to store is where is the first node and where is the last node. We've discovered that the null pointer will start us off and make a good version of an empty list, right? An empty list will just make everything null. That's what we'll do. Make first and last null, and we'll check against that. That's how we know that our list is initially empty. And then if we add stuff, we have to change first and or last. So we learned how to do push front last time, which was you make a new node, and it's going to be the new first thing. So you take the old first thing and shove it into the next of the new node. So that's what we thought we talked about. Sometimes you also have to change last. If it was the very first node you wanted to push into that list. That's important. Yeah, so that's where we left off. And now I want to talk about push back. All right, so let's do push back. Are we ready for that? All right, so push front involved all these things. Make a new node on the heap. We did all this, right? That one or that one. It's going to hold the data value that you want in it, of course. The next thing is going to be the old first thing, which is perfect. That's what we want. It's the old first is now the second thing. And then the first becomes the new node. That's important. And then sometimes also last needs to change. That's what was push front. Push back is going to be similar yet different. All right, so let's say we called push back on, I don't know, 42 again. And so let's, again, we have two cases. Like, was the list initially empty? If so, I got to change multiple pointers, right? Or was it the list non-empty? So let's have both of those examples again. So like if I had a list and I called pushback on it with 42, L dot pushback of 42, initially, perhaps the list was empty. First, last were both null, or perhaps the list had stuff in it, at least one thing. That will be the more general case. First, last, and let's say it was pointing to the list 1, 2. 1, 2, null. So that's the first node. That's the last node. And so, all right, I want to add this 42 node. Again, we're going to play that same game of, well, we got to make a new node on the heap for sure, right? Make a new node on the heap, have it hold the data value we're trying to put there. So 42, 42, put it over here. That's always the first step, right? What's the next of the last node in a list? What comes after the last node in the list? What goes in the next pointer field? All right, yeah. So that's already different to push front, isn't it? We're not just like take whatever was in first before. That's now the second thing. It's just like you're adding a new last node into the list. So the next pointer for your new node is always going to be null, isn't it? That's interesting. That's new. And then, okay, then we have to think about some things. All right, so what's going to have to go on here? Well, let's do the general case first. 42 is now the last node. 42 is now the last node. I have the old last node. It was this one. I can get there through last right now as long as I haven't changed last yet. So go there, go to the old last, and set the next pointer of that last element to 42. Yeah? Go and do that, please. That's what I'd like. So go and do that. And then I can change. I can say that last is now this 42 node. Does that process make sense? That's kind of what you're going to do. You're going to go to the old last node, say that its next is now the new node that you're making here, because that is the new last. So that pointer has changed. Now last can correctly become that last node. Okay, so that I think is what I wanted to say. And then for the other one, okay, again, you're going to play this game of, well, you're going to try, right? My old last's next needs to be me. I'm the new last. You're going to have to check against null because you cannot go and dereference last's next right now, can you? That would be a seg fault. So you do have to be careful in the empty list case. Like check and see, hey, is last something I can go into right now? If so, I can play this game. If not, just be like, all right, the list must have been empty, therefore first and last must be null together, which means first and last must change to be my new node. So that's kind of going to be the process. All right, so check against last. If last is null, you know the list was empty, right? First and last must be both together null. You can do this. Otherwise, you do this way. Okay, so that's more of a diagram this time. Less words, on paper at least. Questions about that algorithm? You see it? All right, I believe in you. So that's like normal insertion. You got to the front, to the back. Linked lists are good for inserting anywhere. Like if you want to put something in some random spot, here's what you need. All right. So if you have, I really would like this node to go in the middle somewhere. If that's your goal, here's how you can do that. You need something, right? What do you need in order to add something somewhere? 1, 2, 3. So here's your list, let's say. And let's say I'd really like to add like the 2.5 node, keep this sorted right in between these two guys. I'd really like to add that node. So what you need in order to make that happen is you want a pointer to the previous element, the place where you, right before you want to do the insertion. You want to insert after that thing. So you want a previous element pointer. So call that n or something. You need, in order to insert the 2.5 node successfully, you need this node. Does that make sense? Because then, I mean, you can get its next, you can get the thing that should come after, which is the next of this one now, through its next pointer, and then you have to set its next pointer into there. So like you need that previous node that gives you everything you need. You can't like have it start here because you would have needed to go backwards. That would not have worked out. So yeah, as long as you have a pointer to the previous element, you can say, okay, the order is very important here. You can't just like immediately chop off this and say your next is that, because now we don't know where the 3 node is anymore. But if you do it in the right order, it's like, all right, the old next of that node is the new next of this new node. So take that same address, put it there, and then you can finally chop this one off and say, no, the 2's next is 2.5. So the order is important. You don't want to forget about where the 3 is. Don't chop off this particular next pointer early. But as long as you do it in that way, you're golden. All right, so you just need a pointer somehow to the previous element, the place before you want to do the insertion. You're trying to insert after that node. After you have that, everything's happy. Okay, so that's just like insert at the front, the end, and any other place. Questions about those algorithms? All right, so I don't know the best way to show all this to you. You have the slides from last time, technically, if you want to go look at those. But I have a question. All right, I have a question for you now. I'd like you to think about in groups. Please get together, say hello to people, and try to figure out the worst case running time complexity and space complexity of doing push front and push back. All right, do not, if you get the slides, don't look to the future slides because that kind of gives it away. But here is, I'll give you these diagrams kind of. Here is push front, reminder of what's happening there. And then push back, we have decided was this. These ideas. So come stare at the screen. It's going to be a little small, sorry. Those are those algorithms in picture form. Can you extrapolate? What's the worst case running time complexity and space complexity? I did some color coding, which is nice, I guess. Where, let's say you're probably going to need a variable, potentially. You may need a variable for your algorithms. Let's say that we always like to use capital N usually. Let's say that N is the current length of the list, if you need that. If that factors in somehow. Current length of the list, please use N for that. All right. And then I'd like you guys to try to write it down if you can. So space complexity and running time complexity for push front and push back. Are they the same? Are they different? Let's find out. And make sure to do attendance, please. I'll stop that when I think about it again. Now let's go to the written nice page, and I'll clear it out. And yeah, I'd like you guys to please try that. Are there any questions about the question? You think we can do it? All right, please take a few minutes to say hello to the people next to you and think about this. Get your answer.
Yeah, I definitely remember your face. I don't think we ever really talked much. We're talking like in case of ego. I think it's all fun. But we're talking about common steps, Rich. Yeah, it's like no matter how big the list is, you just need to head and tail or push back, push back. So you instantly jump to where it is. No. You're touching things like that. Yeah. Well, I guess we will. US elements were under so yeah, I agree with that. It's definitely gonna be important.
A couple more minutes to discuss. We got plenty of time.
This is good too. Sorry, sorry.
Let's take maybe another minute. Does that seem like enough time to finalize things and get an answer in? One more minute. Let's try. All right, a few more seconds. Get something in. Press that submit button, please. All right, let's see what we're thinking. Don't cheat and look ahead, but you could have, I guess. Let's see what we think. Ooh, look at us. We're thinking constant for both. All right, and we all agree, it seems. Nice, 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 nice. Thank you for that. Let's see. Let's see, I promise to stop that. Let's see if we're right. I think we are. Do I need to get any of the... No, I have the next slide to do it. Cool. Let's talk about it. You are right. So let's figure this out. So the running time for insertion is going to be constant because all it's doing is moving some pointers for a couple notes. It's never all the notes. You don't have to shuffle anything over like you may have had to do if it was an array. This is why we have linked lists. Beautiful. So yeah, that is lovely. And let's do it. So let's yeah, everything's constant time. I'll prove that to you. We'll go back to the push front slide to prove it. And that was when we did like this example of like we had a list. We said L dot push front 42. So you started with a list that maybe had stuff in it. Like you're not adding that to your space complex. Like you started with that. You did not. You don't have to keep along the whole list as you analyze. It's just like what did push front add? That's what you analyze for space complexity. Space complexity, if I can talk today. And then the 42 is just a single int that you're getting as a parameter, and that's only one always. So okay, we got push front. Let us add some numbers here. So what do we got to do for push front? Because I've spelled it all out. It's more or less the same for push back, just like a different kind of if statement maybe in a different order. Make a new node on the heap with the supplied data value. That's actually the one piece of, or I guess we're talking about running time right now. So let's just deal with running time. So like, what do? You say new. That's to make something on the heap of a certain amount of space. That's like what? 4 bytes plus 8 bytes for a pointer. 12 bytes total. So that's a constant number of things that it needs to do on the heap for you. And so it goes through and it does it in constant time. Also constant space, but we'll get to that later. Then you got to bring it to the front of the list somehow by saying that, oh, my next is the old first. That's a line, right? A line changing some pointers. And then first equals my new node. It's like 2 lines. 2 lines doing constant work on each line. All right, so that's really not too bad. So those 2 pieces right there, those are those 2 lines. Change the next pointer. Constant time to mess with a pointer. Constant time to mess with another pointer. That's pretty nice. And then if the list was empty, so you have to do a conditional, check it and see if something was null. That's a simple check, right? That's constant time to do the check. If that's true, you go into the body of that condition. You have to change also last, which is just another line messing with the pointer, and that's still constant time. So all of that is constant. That's beautiful. You just add them all up, right? Add them all up. A bunch of constants is still a slightly bigger constant. Yeah. So that's lovely. That's why it's constant time, and for a similar reason, it's going to be constant time for pushback. It's just messing with some pointers. You can see the green stuff, right? That's what's changing. That's the new things. And it's going to be the same for space complexity. For space complexity, all that you're adding to the thing is, I mean, you have the parameter, I guess, during the call, which is 1 int, so a constant int amount. And then you're also making a new node on the heap. Potentially needing to, like, for a split second, give a name to that thing. So that's like a separate pointer variable. Like you're calling this n for my new node or something like that. Like that's a thing. But that's still a constant amount of space. You're adding 1 new node, and that's not like some arbitrary size. It's a constant size. All right? Does that make sense to us for both space and time complexity? That's not too horrible, right? That's lovely. So, yeah. We're experts. Do yell at me if you have any questions about this, but I want to move on now to some other questions. So let's think about this. Searching, we kind of figured this out before. You're kind of forced to do linear search for a even a sorted linked list, because you can only go from starting from first. You can only follow next pointers. You can't move around haphazardly. You can't jump around. So let's say we have a list and we'd like to find something in it. That can be our search operation. So I guess first is all we really care about here. 1, Our list is 1, 2, 3, my favorite list. And all right, what do we need to do? Let's say we're looking for a value. In the worst case, right, it's nowhere at all. We have to look through everybody. And we can't do it, even if it's sorted, we can't like start in the middle and do some weird binary search game. We have to start at first. That's our only window into this list. Okay, so what we have to do then is like we have a pointer. We start at the first node. We have some like node n pointer. You start it there. You look at its data. Like, hey, is n's data equal to value? If so, I found it. If I didn't, keep going. And so in the worst case, you keep on going, right? That's not 1, it's not 2, it's not 3. You get to the end, like, all right, n equals n arrow next. You get to the null pointer, like it's pointing, and it's pointing nowhere now, it's done. Once you get there, you're done with your loop, you didn't find the thing, and you went through all n of your nodes, if we're counting that with a capital N, like we like to do. So for time complexity, it's like this, right? Worst case, you have to compare against every node in the list, which is linear time complexity. Even though it's sorted, you can start in the middle and do binary search. All right, so does the time complexity part make sense to us? You got to go through that whole list no matter what, even though it's sorted, because you can't start in the middle. You have to only go through first. The space complexity here is constant as well. Constant, just like this last step. So because we're not like adding any new nodes, we're just, I guess all that we have is like the memory it takes to hold our parameter value that we're looking for, and then also our little local variable n that's moving through the list. Those are kind of the two variables we need. So like a pointer and an int, that's a constant amount of space. Yes. So that's not too bad. So it's constant space complexity, can't do any better. Linear time complexity, that's about as good as you get for a linked list that only has next pointers. All right, so that is searching, and that's, I hope it's not too horrible, right? I think you could do this once you get practice. Any questions about this one? All right. Let's talk about deletion now. That's the harder one. So we're going to talk about, I'll ask you about its complexity. I'll have you analyze it with my pretty drawings. But there's going to be, like, let's pretend we only want to ever delete from the start or the end. Like, those are the options we're going to give to the user. But you can think about it in the middle later. We can maybe talk about that. But let's say that we had a pop front to remove the first element and a pop back to remove the last element. So let's see what that's going to look like. All right, there's going to be some steps. So let's do a drawing of pop front. How do I want to think about this? Well, let's do the general case first, maybe. Yes. Let's say I've got a list. And it's got a first and a last. And it's got some stuff in it. First and last. We'll come back to the other cases. The general case is usually the easiest one to think about first. So we got a list with actual things in it. I guess this doesn't really apply, but if you think about it, right, our list could have been empty, and we're trying to pop it. That was the user's fault, I guess, but you don't want it to like crash the program. So you should probably be checking against first, right? Because you're going to be looking at first and trying to get rid of it. So make sure that first isn't null before you try to do anything else at all. That's important. Okay, what needs to go on now in order to remove the first node? So essentially, we want to get rid of this one and make that one the new first, kind of. The next thing, the new first. So there's an order to this. So, okay, what do we need? We need to, make first's next node the new first. So we had the old first, it's this one. We need to make its next node the new first, this guy. Because, and that's step one. Like, make this happen in the first step. Do not yet delete this node. Give it a name so you can have it later, like old first or something. Call it something for a split second because you need its next pointer. You need its next pointer. Mess with the old first, make it this one, because now you can delete it. You cannot delete this node and then try to go through its next pointer, could you? That would not work out. That's bad. That's undefined behavior. So those are your two steps. All right. So that's going to be step 2 is get rid of the old first, something like that. Does that make sense? So you need to go through it in that order. You could not have this be step 1 because then you'd need that next pointer in step 2, and that would just not work out. Okay. So those are your steps in that order. So make first's next node the new first, and then you can delete the old node to get rid of it because it will have been made on the heap. Okay. So there's that. And so that there's already one special case that we kind of talked about. If the list was initially empty, you couldn't have done any of this. So there needs to be an if statement surrounding this idea. That's step one. And then there's even another special case. There's a size, the list just got down to size 1. Let's say the list looks like this now. Let me redraw it, actually, just to drive that point home. Whee! That's about as good as I can do. So let's redraw that list as it looks now. So this is my list. It's got just the 2 node in it now. First, last. Whee! There it goes, there it goes. And it's got just the 2 node. Next is null. So you gotta be very careful when the list has length 1, because what's about to happen? If I play this game, all right, first is not null, we're good. To get rid of it, we're gonna set firsts. We're gonna set first to be the old first's next node, which is null, which is fine. That's good, actually. That's exactly what we need, because the list is now empty, right? And then we can delete the node. But last, yeah. So that's what we forget about. If your list became empty, you will notice that through your first pointer. And so once you're done with all this, like, you better check for that. Hey, is first now null? If so, last is pointing to a node that I just deleted. Does everybody see that? So once your list is size 1, the first is the last, and then you run into trouble there. All right, so first and last both need to become null. If you just made first null, you better have made last null. All right, that's the idea. So you chop off these kind of pointers, make them become null. Okay. Does that that idea make sense? Any questions about it? All right, so that's the secret there. And now let's say the list is empty. If you call pop front again, like just check that first is null, making sure that you don't try any of this stuff. All right, so general size list, you play this normal game, check against first always before you try anything. But step 1, step 2, if the list is size 1, you got to worry about last. If the list is size 0, that was just like you return if it's empty. Do nothing at all. It's already empty. So that is pop front in a nutshell. Any questions about those diagrams? All right, let's have an idea of pop back. So pop back is very similar to pop front. It's just like the ideas that we talked about with first become ideas that we talked about with lasts. But there's also a little bit of a trick. So let's think about that. So pop back looks like this. Let's do the general case, because I think you can imagine the special cases now. Pop back. So let's say that this is my list. It's got let's do 1, 2, 3. We got the list 1, 2, 3. So 1 is the first node. And last is the 3 node right now. So if we're popping the back, what needs to happen? Well, in diagram form, it's not that hard to think about. It's just like, all right, this is the old last. I would like to get rid of it. The order doesn't really matter because you're not using this to get to the previous thing, right? There's no arrow going that way. So like, you need to get rid of that node and somehow make this guy the new last, right? So you need to get to here somehow. Does that make sense? You need to get to that second to last node because that's the new last. Does that make sense, everybody? You got to set it in that way. So you have to get to the second to last element. And so that's like, how do you get there? You cannot start from last and go backwards, right? So you better start from first and make your way that way. And figure out like, all right, am I at the second to last node yet? If not, keep going. There's an if statement that could do that. Okay. Does that idea make sense? I'm going to ask you a question about complexity soon, so I'm not going to say the complexity, but I hope you can kind of see that what's going on in pop front and pop back, kind of similar yet different. All right. Questions about pop back? Kind of see what needs to happen. It's just like last needs to change. And then again, you have the same problem. Like if first was last, you just deleted one node, you made last null, you better also made first null. Stuff like that needs to happen. Okay. So let's do a general deletion example now if we're ready for that. It's like we have a node, I want to get rid of it somewhere. So let's pretend we've got somewhere in the middle that we want to remove. And let me walk you through what needs to happen there. It's very similar to like I want to insert in the middle. What do I need? I'm going to need some pointers to the previous element again. That's probably enough because you could also get to the next element through that. First, last, in general, let's say we got the list 1, 2, 3, and I don't want to remove the first node or the last node. I want to remove somewhere in the middle. Let's say we want to get rid of the 2 then. Something like that. I would like to get rid of that 2 node somehow, please. So the process is going to be, you have to do a search, I guess, because you're not immediately, like somebody could have given you a pointer, but they would have had to find it through searching anyway. Like, where is this node you want to delete? So search for it, go and find it, and maybe it was in the middle somewhere. All right, so you need to know that that node exists. You got to iterate to it, I guess. And then also, you need to know who came before you, because like that needs to happen. You need to make it like hop over the one. That's what needs to go on. So you're going to need a pointer to the previous element in the list. So as you're iterating, like you're looking for something, you better save like a previous and an next and like iterate them in lockstep. Does that kind of make sense? That's what's going to need to happen. You always need to remember who came before you. It was like previous equal, like if this was not the 2 node that you're looking for, you need to kind of like do that. That's how you can play that game of always remembering who came before you. Like you just like let previous be a slower moving pointer. That's what needs to happen. Let's see. So that needs to go on like that. And we can analyze this one. I think that's not a big deal. Do I want to think about that right now? Maybe. Yeah. So yeah, we'll deal with that in a second. So once you have these pointers, like you have the previous thing, you have the node that you want to delete, here's what needs to happen, right? You have to say, okay, I don't want this node anymore, but before I delete it, I better remember who its next was, because that's going to be the previous node's next now. Does that make sense? So that's kind of like step 1, and then step 2 is now I can delete this node. Nobody cares anymore. It's not gonna. I'm not going through weird things. I saved that pointer to that other thing, and I've made it hop over correctly now. Okay, so that's like the general case. If you're searching for something and you noticed that it was the first element, then you have to play the pop front game, and then like maybe first and last both need to get set. So there's a special case there that turns into pop front. But in general, that's what you need to do. You need to search for the thing you're trying to delete, which we know is going to be linear time, and then you mess with some pointers around that element where you want to delete it, including the previous thing, okay, which is going to be constant work there. So the bottleneck was kind of searching for the thing you wanted to get rid of. Does that make sense? So that would be that space complexity. And it's interesting, or sorry, that time complexity. And it's interesting to think about space complexity here because it's like, is it negative space complexity since you're getting rid of something? Nobody really says that in a textbook, so we don't count it like that. But it's going to be like constant space because you got some pointers and that's about it. Okay, we don't really count deletion, I don't think. So yeah, I think that's the general process. Yeah, sometimes it turns into pop front though. Any questions about that? All right, so I have another question for you now. So we have talked about some algorithms. We've got pop front and pop back now. I've drawn some pictures. I would like you guys to think about just the running time complexity, please, of pop front and pop back, and I'll give you a few minutes to discuss again. So if you're already on that written nice page, I think that's a good place to put it. Please refresh the page so that I can like zero it all out again. And you can elect a new leader to talk about or to answer this and figure out just running time complexity. But if you'd like, I can give you these screenshots again of like at least the picture form of what's happening. They might be a little small though. There's that one. And that was pop front. Pop back was this one. Give it to you as big as I can give it to you. All right. Any questions about the question? So pop front and pop back, running time complexity. That's all we need. Where let's say that n is the size of the list again. If you need that, use the letter capital N, please. Okay, ready? All right, give that a try. I'd like to see what you're thinking there. Still got plenty of time. Think about it. I did stop it, so you're gonna have to talk to me at the end. Oh, so
Thank you.
just remind me.
Yeah.
Another couple minutes to think about it. Like, how would you code this? Think about it in C++ if you need to. What would it look like? All right, that seems to be my timer. Almost prevented the sound. Was that enough time to think about things and get an answer in? Best guess. Let's figure this out. Let's figure this out. What are we thinking? Ooh, look at us. We think that there's a difference. I do believe there is. Do we look ahead? Do we cheat? No, I think we probably got that out of the picture. Good. So there is, yeah, it's like it's easier to do pop front, surprisingly. Pop back is harder. Let's figure this out. So you're right about that. What do we got? Well, let's analyze. What are we doing in pop front at least? Where's that picture? Dun, dun, dun. We're doing like a comparison against like first, right? We're doing a comparison against first. We're messing with like getting that next pointer out, messing with the first pointer, and then sometimes also messing with the last pointer, controlling that with another condition. So it's always, we're never like iterating, we're never looking around, we're just always doing a constant amount of work. All right, so that's kind of what pop front was doing. It's like we got a couple comparisons, that's constant. We might only need one of those though. But in the worst case, we'll use both. You're gonna move some pointers around, make the old second thing the new first thing, and then you gotta say delete, and delete is constant time. You just add all that up. Just a bunch of constants. So it's still constant, which is nice. Alright, so constant running time for pop front, but it's gonna be linear time for pop back. Because we need a second to last node. We need that second to last node because that's gonna be the new last node. So if you had a very long list, and so I purposefully only drew a size 3 list just to make sure that you're awake. But it's going to be linear time. If it was a 1 million linked list, you got to iterate 999,999 times, don't you? There's first, here's last. That's first, here's last. Because the new last needs to become the second to last thing. There's no way for us right now to get, like, last needs to turn into this guy, and then we delete this old one. There's no way for us to go backwards. We do not have a previous pointer. There is a way to make a linked list that keeps track of next and previous pointers, in which case this would become constant time. That's what your C++ standard library list does. They're nice like that, but it's a little more complicated. I'd rather have you just implement a singly linked list in this class. We don't have those previous pointers, so we got to start from first, get all the way to that second to last element right there. That's how we figure out where it is. There's a condition that you could use to be like, hey, is the thing after me, is its next null? Something like that's going to be the question you ask to notice if you're at the second to last element. And then you find it, you set it, and then now its next is got to be null. That's the last thing you do to put that in there. Yeah, that's more or less the right idea. Did I actually draw that properly for this one? I don't remember. Oh no, it's fine. It should be okay, I think. So yeah, that's what's going to go on in pop. This is pop backland. Yeah, I did forget to say that. This is the new last, and it's got to be a null next pointer. Excuse me. So that's yeah, that's what has to happen there. And so it's going to be linear because you got to get you're doing a search essentially. You're doing an iteration to the second to last node. You got to iterate through your linked list n-1 times essentially. So that is unfortunate. So that's what gives us O of n. Okay, and yeah, it's going to be constant space for both. You're just like you're moving around your list potentially. Even this one, you just take one pointer to do that moving, and you're saving like what was the old first node, what was the old last node, and just a constant number of variables. And so it's going to be constant space for both. Okay, any questions about any of that? It's not horrible, I don't think. Let's see, what do I want to do here? Yeah, are you ready for a completely different idea now? Because let's say we've implemented all this. We've made the list class. What do we say that looks like, right? We've made the list class with a first and a last, and we've given these operations like push front, push back, pop back. Like we have all those things now. Are we ready to talk about the big three for linked lists? Because that's disgusting. It's not going to be fun, but we need it, right? It's very, very important. We know that now. So, all right, let's figure this out together. You need a destructor for your linked lists, for sure. You got a bunch of nodes on the heap. You better get rid of them as your list is being deleted. All right, so what do we got to do for our destructor? We've got a list. We need to go through it, all right? Well, here's my tiny list. I'll draw a bunch of tiny lists on this slide. We've got a first and a last pointer. And let's say we've got like, this could be drawn better. Boop, boop. Let's say we got 1 and 2. So all the things you made, all your nodes are on the heap, shiny and new. You said new every time you pushed. Yeah. So when you're destructing, let's say that this is the current state of memory. When the destructor gets called, your only member variables are first and last. You need to go through them. You need to iterate through your list and delete every single element. All right, somehow. So these are the things that are deleted in the destructor. And you do need to be careful about that. Boop, boop. So these are deleted in the destructor. You have to iterate through your entire list. Every node that you've ever made, deleted in the destructor. You got to get rid of. Yay. And there's a method to it, right? You can't just be like, I'm at this node, delete it, advance. Right? Because then you lost the next point. That's undefined behavior to go through a node that's been deleted, right? So you have to save like next is that before you delete your n, then you can be like n equals n arrow next, something like that. So it's kind of the opposite of the previous things for the general deletion case. You got to like move your n variable and the thing after it in lockstep, kind of, or just save it. Just save it right before you need it, something like that. Does that make sense to us? So there is an order to it. You cannot go through to something that you've deleted, so you better save where you're going next before you delete that previous thing. All right, that's going to be the setup there. That's your destructor. So how many nodes you need to delete? All n, right? And so you're iterating, you're spending constant time per node. That's going to be an O of n linear time algorithm, isn't it? You can't get around that. You got to delete all of your nodes. Constant work per node, like I'm at a node, call delete on it. So it's linear time to do that deletion. Okay, so that's the destructor. Any questions about that one? That might be the easiest one. Now let's do copy constructor. So okay, this will be fun. Copy constructor. Let's say we've got another list already. Like we've got a list L1. With a first and a last, and boop. Let's say there's 2 nodes or something. So this is an older list. I've got that, and I come along and I say I would like to really make another list L2 based on L1. Boop, with a copy constructor call. And so what needs to happen in L2's land, it's got a first and a last, and this is a constructor, so like first and last are garbage right now. We got to set it all. What do we do? I'll draw in green what we do. Well, you have to iterate through the list you want to copy. So you're going to go through L1, you're going to iterate through it starting from first until last, aren't you? You got to go through the whole thing and insert into yourself every value you see, right? A deep copy. You can't just be like, oh yeah, my first is that guy's first. It can't be like that. My last is that guy's last, because that would ruin everything, right? Then you try to push back to one you've now pushed back to the other in a weird way. So you got to worry about that. You want a deep copy. I'm going to make brand new nodes 1 and 2. Okay, does that make sense to all of us? 1 and 2, and that's our first, that's our last. You could make this easier on yourself if you think about it. You've worked so hard to make a pushback function or method, right? You can call that on yourself. Just do that. You're iterating through this list. See the 1 pushback 1. See the 2 pushback 2 to yourself. Does that make sense? That would work. That's perfect. You do have to be careful to create the list in a way, though, because this is a constructor. Nothing has been set. First and last are garbage at the start. If you want to call pushback on yourself, you better make the memory look like a list that starts out empty, yes? So you should maybe set first and last to null before you try to call pushback. Yes? That's very important, because if you didn't do that, who knows what's going to happen. Garbage in, garbage out. So worry about that. Yeah, just like make them start at null. And then you can start pushing back to yourself. What do I want to say there? So like, here's like the way that the memory would look if you did it that way. So like initially, the first and last, you started them at null. You have to do that yourself. Then you call pushback on the 1, because like you're looking at the 1, you're iterating through it. And so that makes the 1 node. Now first and last, its next is null. First and last become that. And then you push back the 2, which means you make the 2 node. It's going to be having a next of null, but the 1 now, the old last, is going to point to the new last, and we're going to chop off that point and turn that in. But you've handled all that in pushback, right? As long as you start the memory off in a way that pushback understands, you are golden, okay? So I think that's most of what I wanted to say. So that's what the copy constructor is going to look like. Does that make sense to us? So let's analyze it. We've got some other list, right? So now we've got like 2 lists in the picture. They're going to have the same size though. But let's say like the list we want to copy has like L1. Let's say it has N1 nodes. Like, it doesn't have to be the same, especially with a copy assignment. We're going to deal with that. And so you're iterating through that entire list you want to copy and calling pushback every time. Pushback, we know, is constant time. All pushing is constant. So that's good. You're going to call it, though, n1 times. For every node in the other list, you're going to call it that many times. And so it's constant times the size of the list you're trying to put into yourself and make a deep copy of. So that's going to be O of n1, like the size of the other list you're trying to copy into yourself. That's going to be the running time analysis. Does that make sense? Questions about that? You're going through that other list and pushing back all of the elements that you see. Okay, so there's that. What else? Yeah, I think we're ready for copy assignment now, because that's the most complicated. It's got aspects of the copy constructor and the destructor all at once, right? So let's figure this out. Okay, so let's say for copy assignment, it's mostly the same as the copy constructor, but we have stuff in ourselves already, and so we have to delete the old stuff and bring in the new stuff as a deep copy. Also, remember the self-assignment check. That's constant time to do, though. So we need another slide to draw all that stuff. So okay. We've got, we have two existing lists. We've got L1, let's say, and L2. It's got a first and a last. L2's got a first and a last. And I don't know, let's say that L1's got 1 and 2 in it. And L2's got some other values that we don't care about anymore. We're trying to get rid of them. So let's say it's got like 3, 4, 5. 3, 4, 5, and that's its last. And then we come along and we're like, oh, L2, I'm sorry. I guess I'm using subscripts. You can't really do that in actual code, but we can right now. We come along, we're like, you know what, L2, I would like you to be a copy of L1 now. Copy assignment call. All right. So what must happen, right? First, self-assignment check. Make sure you're not being like L2 equals L2 and you're about to delete everything. That's important. And then, okay, it's L2 that's changing now. All right, so I'll switch to green for what's going to happen here. So self-assignment check, you have to get rid of 3, 4, 5 don't matter anymore, do they? We are done with those guys. Does that make sense? That's what we want to get rid of and do here. So let's, you could be slightly smarter here. I don't even want to get into that. Just like the standard idea is like, you have all these things already, just get rid of those things. So get rid of these things. So it's going to be the same kind of process in the destructor. You cannot, it's bad practice. You could call the destructor on yourself. It's a weird way to do that. I'd rather you didn't. Just like copy and paste the destructor code kind of here into the copy assignment. So get rid of your other nodes. And then you could play the game of the copy constructor, right? So start the memory in a way that you're going to iterate through this other list and call pushback on all the things you see. So like get rid of all these nodes and just like set first and last to null. Yeah, that would work. Okay. Another way to do that and do the destructor is just like call pop back or pop front on yourself in a loop until your size is 0, because you're going to have a size method, right? Something like that. That might be a little, that could turn, depending on what you do, that could turn into quadratic time though. So you need to be careful about that. So yeah, get your memory in a way that you could like call pushback, pushback on yourself with the other node stuff. And then you'll bring in your new stuff. You'd be like, all right, push back the 1, make the 1 node, push back the 2. It's always use the stuff you've made for yourself if you can. So there's that. But you got to start the memory off in a way that pushback understands. So there's those. And that's kind of what's going to happen. So self-assignment check, delete your old stuff, bring in the new stuff just like you did with the copy constructor. So it's kind of like destruct plus copy construct. Any questions about the process? So it is a little weird, but yeah, the diagrams, hopefully you're getting a feel for the way I'm drawing things, like, and you can do that in code now. So now the analysis time. Oh man. Okay, well, we got 2 lists, right? We have this list and our old original list, potentially of vastly different sizes, right? So who knows which one was bigger? L1 had, let's say, N1 nodes. And L2 had original L2 had, let's say, N2 nodes. All right, okay. Well, How am I using these variables is now the question. Well, we've got, we're going to delete our current stuff, right? We're going to delete our current stuff, which is going to take how much time? It's going to be essentially a delete call for every node in our original list. So it's n2 calls to delete. So that's an O of n2 process. Does that make sense? So that's the deletion part of our self. That's going to be O of n2. O of n2. That's the first part. And then we do the copy construction idea of like push back as many things, like zero out our first and last, and then push back as many things as in L1, and there's n1 things there. Calling pushback is constant time. We're going to call it n1 times. So it's going to be O of n1 to deep copy it into ourselves after we've zeroed out ourselves to nothingness. Does that make sense? So now it's O of n1 work to bring in the new stuff, to copy it over. So O of n2 for the deletion of ourselves plus O of n1 to copy over the other thing, and that's way too small. Here, I'll do my best to make that smaller. So O of n2 for the deletion plus O of n1 for the copy in yourself stuff. And now the question is, which one is bigger? We don't know. Sometimes n2 is bigger and it wins out. Sometimes n1 is bigger and it wins out in the game. So when you have two variables in your analysis, you can bring them together. So if you're not sure which variable is bigger, just like put a plus sign between them because we are adding them, right? It's going to be like some constant times n2 plus some other constant times n1. It's like bring them in. Bring them in together. You're not sure which one's bigger, so they're both the biggest, potentially. Chop off their constants. That's the analysis. So this turns into, then, big O of n2 plus n1 or n1 plus n2. Doesn't matter. Plus is commutative. So that's the analysis. We're not sure. It's like you're doing n1 work and n2 work. Who's bigger? I don't know. It depends on the lists. They're both variables. Keep them variables. Okay? That's your copy assignment. That's the most work, kind of. Are there any questions about that? You see it? That's the most complicated, for sure. Because I want to switch gears one last time. Are we ready to switch gears to just like go back to code for a second? We need to learn how to use linked lists some more. But yeah, big three. You will be implementing this. You will be taking these diagrams and making them happen. So if we're ready, I want to talk about recursion on lists because of course you can do that. All right. So here, just to blow your mind one more time today, let's talk about going through algorithms that are recursive on lists. So the standard way of doing it is you have some algorithm you want to run on your entire list, and there is somehow a way to break it down. There's a way to break it down into like running on a smaller list, because that's what it would need, right? For recursion, I want to do the same thing in a smaller way. We can actually break down the list itself into a smaller list. So just like we broke down an array into a smaller array, we're going to play that exact same game. And that's one of the reasons why I taught you how to do that. So the question now is, if this is the biggest list ever, does anybody see a smaller list here? There might be multiple. Can you see it? So a list is always represented by a pointer to where it begins, right? So you could think of this as a smaller list. Do you see it now that I've pointed it out? Just give me a pointer that starts not at first, but at, like, I don't know, call this L. Then from L's perspective, that is the entire list, right? Does that make sense to us? There's a smaller list. I can chop off that first node and make a smaller list, essentially. I don't have to delete it. Just like consider it from like this is now the start of it. That's a smaller list. There it is. You do have to be careful though, because not everything's a smaller list. Like this for sure is also a smaller list. Like started at 3, that's fine. But this right here is not a smaller list, because the last element of a list should always be null, right? And that's not true for this box thing. So do you have to be worrying about that? But like you can always go that way. This is a small list, that's a small list. The null pointer by itself is an empty list. That's all fine. Okay, so that's what you can do. And that means if you have a smaller list and you have a recursive problem, you can call yourself on that smaller list that's inside of you, and you're guaranteed, right, to get back the answer for that problem on that smaller list. And as long as you factor in its answer plus the thing you didn't yet consider, which was your first node, as long as you somehow build up the bigger answer using that correctly and return that, the recursion will work out. Okay? So yeah, just remember that linked lists are represented by a pointer to their first element. That's all you need to pass around a linked list. Just say where it begins, because you could follow next pointers all day long to get to the end then. That's all you need to pass around a linked list. That's how you represent it. That's how you pass it to a function. Okay? So does that make sense to us? Like, that's how you can break down a list. You can give it, just like say where it begins. You can make one smaller list that way. All right? Okay. So let's do this algorithm. I've got this list, 1, 2, 3. I would like to recursively print this list in order, like print all the elements in order on a line. So like I want to produce the output 1, 2, 3. It's a very complicated program that's going to print 1, 2, 3. So okay, if this is a recursive algorithm, I claim it's a recursive algorithm, I can break down the list this way, right, into the first node and the rest of the list, the smaller list, one smaller list, and this is what I'm going to make my recursive call on. First, if this is n, if my original list was represented by n, how do I pass around the smaller list? Where is this node? It's n arrow next. That gets me here. Does that make sense? Because it's just like, where is the address of that other list? Is whatever this address is right here. That's n arrow next, isn't it? So that's how I get to this list. That's the beginning of it. That's how I can pass it around. And so, okay, remember that what will happen is, all right, I make this recursive call. It's a smaller thing. I get to, through the magic of recursion, I get to just believe that it's going to do the right thing for this smaller list, which is printing all the elements in order. So the recursive call gets me here, gets me the 2, 3 printed for sure. I'm happy. You get to assume that that works. As long as you do everything else right, it will work. It's beautiful. So recursion guarantees that your smaller call will do the right thing on the smaller thing as long as you build up the rest correctly. So like print in order on the smaller thing, there's your recursive call. You're passing along that smaller list by a pointer to its beginning. You're guaranteed that that will print exactly this. What do you need to do to fill it in and get the final answer? It's just like, consider the thing you haven't used yet. The 1. The 1 also needs to be printed in order. Does it happen before the recursive call or after the recursive call? Before. You see that? Take your current nodes, n's data, print that out, and then make the recursive call. Call yourself on the smaller list. All right? So that still might be a little vague because we're not very comfortable with recursion and the linked lists are brand new, but I'm going to prove it to you. All right? So you need to print your first element before making that recursive call because it needs to appear in the output first before the other things take over. Okay? So that in theory is the idea. And so that's the recursive case. You have a smaller list to go through. The base case then naturally is, I don't have a smaller list. I can't chop it up anymore. So the smallest list you could possibly have is the empty list. And if you're trying to print everything in order, what happens if somebody gives you an empty list and wants you to print all the elements in order? You can just be lazy, right? And just do nothing at all, and you don't have anything to print. So you'll check against like, hey, is my list nothing? So like, is my n null pointer? Because that's what represents an empty list. There is no beginning, all right? So that's what you'll check for. So let's make this in code and go from there. So I would like to make a file. Let me copy in last time's actually the list that was 1, 2, 3 because I think we did that, right? 9, 1, 2, 3.cpp. And I'll call it linked list recursion here. All right, so here's 1, 2, 3. I've made the list 1, 2, 3, and let's make. We're gonna call our. I'll get rid of the printing, I guess. We've got a first and a last. We're only gonna need first here. I'm gonna make a print in order function that takes a list by a pointer to its beginning. That's all you really need. All right. So lists are represented by or with pointers to their first node. All right, so that's what it is, and that's how we're going to call it. So let's make that happen then. So I've got a list, and I'll call it print in order. That's my function, my recursive function. Print in order, and it's going to take an entire list by a pointer to its beginning. We'll call that n. All right, and so we're either in the base case or the recursive case, and we want to print in order. So if my list is empty, that means the list that I was given starts with nothing. It's a null pointer. That's its beginning. That's its whole thing. So that is the base case. That's the empty list. That's how you know when you've got nothing at all. We're representing the empty list by null. Empty list. You don't have to do anything. Do nothing. So you could have just had one if that was checking the other thing, but this is kind of fun. You can have an empty body. Otherwise, if n was not null, that means I have a list with at least one node. That's concrete that I could actually go to. It's not null. So recursive case. I have an actual list that I can chop up at least. I get a next and have a smaller list. So what do I have to do in the recursive case? I have to eventually print the smaller list, right? Eventually I have to make a call to myself on the smaller list. That's a call to print in order, right? What I want to do is print my first node's data, right? That's the one that's not part of the smaller list. So print the first node's data. And then I want to recursively print the smaller list. And that is a call to myself. Print in order, like it's my job, but I can pass it off to myself because it's a smaller thing. So that's how I pass the smaller list. N arrow next is a pointer to the next node in the list. And if I represent a list, right, as a pointer to its beginning, that's a pointer to this node right here, the 2. And so from this call's perspective, that's where the list begins. And so it's a one smaller list. All right. So that's the recursion. You get to assume that that's going to do it properly. It's going to correctly print the 2, 3, as long as we print the 1 before it, right? That needs to happen before we make that call. So print the first node's data first, which is just like cout ends data. All right, and that's going to be the code. Any questions about that so far? It may just be weird because it's recursion. Something to study. But let me show you that it works. We get the 1, 2, 3. Cool. Yeah, for us. So like we're just passing the whole list by a pointer to its beginning, because that's how we're representing lists, by pointers to where they start. And that's how we pass the smaller list. So that's a later point in the list. So pretend it starts there now. It'll keep playing that game. All right. So we get the right answer. Let me draw the stack for you. I think that would be a very helpful thing to prove to you that this is working properly. All right. And it really does make its way down to the base case, build itself out properly. So we were in main. And I'm going to be lazy here and draw the list a bunch of times. But there really is just one list we've made in memory. It's on the heap. We called print in order originally on the entire list 1, 2, 3. That's what we did, starting at the first node. So we said print the entire list 1, 2, 3. That's how I'll draw a list. So that's what we said. Print that whole list 1, 2, 3, please. And now we jump up to here. And it was not an empty list, so we hit the recursive case. And so the very first thing we do is we print our first node's data for this particular list, which is 1, 2, 3. So we print the 1. The 1 gets printed right now. All right, that's what's happening. And then we make the recursive call. We need to recursively print the smaller list. That's not on us. That's on a smaller version of ourselves. So we're going to make a smaller call to ourselves on the smaller list. We're going to say, all right, to finish printing 1, 2, 3, I need to then go and print. I'm not done. I need you to please, myself, smaller version of me, go and print the list 2, 3. That's what the recursive call is saying. Does that make sense to us? That's what's happening. So it's this call. The first call is stuck on this line. It needs to go and do the rest. Print in order the smaller list. That's this call that it just called, and it's waiting for it. Okay? So now we're in this call. The list, from its perspective, is 2, 3. It's still not empty. And again, we're in the recursive case. So it's going to print its first node's data, which from its perspective is the 2. So this is where the 2 gets printed. 2 is getting printed right now. And then it needs to print the rest of its list because it knows it has a smaller list to print. It will call print in order again on the smaller list, which is now the list starting at just 3. All right. So print 2, 3 is like, I'm not done. I'm waiting on that last night. I need the rest of me printed. Go and do that. Recursion. So now it's going to call print on the list just containing 3. So it's the 3 node with the next pointer of null, which is still not empty. So we're here again. It's still not empty. In the recursive case, we're going to print our first node's data. So n area from 3's perspective, the list starting at 3 is 3. So the 3 gets printed right there. So it really is doing the right thing in the right order. And then it's like, all right, I have a smaller list. I'm not sure what it is. Like it is going to be empty, but we don't know that. It could be a longer list. So we're going to recursively, the 3 nodes like, all right, I've got a smaller list after me. Let's go print that. Print in order please, smaller version of me, the rest of my list. So it's just the null pointer. So it's passing the null pointer, which represents the empty list. So please go and print now the empty list. That's the last call. So everybody's waiting. All these guys, they're waiting on this line for the smaller list to be printed. It's not yet completed. And it's about to, though. So now we're finally in the base case, right? It's like print the empty list. There we go. Print the empty list, please. Base case, do nothing. It just returns. It's done. It's done its work. Nothing to do. And then all these guys were like, yeah, that's what I was waiting on. It's finished now. I got the answer back, or I got the answer, like it's completed. And so like once that's returned, that call can return. Everybody's happy. Like 3 is like, all right, yeah, you printed the smaller list. I'm done now. 2, 3 is like, oh yeah, you printed the smaller list. You gave me control back of the program. That's all I needed. I'm done now too. And so everybody's happy. Everybody returns. And now we're back in main, having done the right thing. Does that make it slightly clearer why this is working?
Yeah.
It is odd still, I know. It's something to wrap your mind around. Try to draw the pictures yourself and come back to this. But yeah, is there anything else I could explain that would make it slightly easier on your brains? Because this is just something you got to force into it. All right. I do have more examples, though. So let's do that. You'll get used to it. So, all right, let's do a recursive print in reverse order. We're going to keep playing this same game. We're always going to chop up the list in this way. So you're going to get used to that. Like, this is my smaller list. That's how I pass myself to a smaller version of me. I'm passing a smaller list. And so, all right, if I want to recursively print in reverse order this list, I want to see the output 3, 2, 1, don't I? And so if this is the smaller list, if the smaller list is 2, 3, I'm guaranteed when I make my recursive call, I just get to assume that I will see 3, 2 printed properly. You get to assume that. As long as everything else works out, it really will do that. So like here's the recursive call, the 3, 2. All right. As long as you build up your final answer that includes the 1 correctly, that recursive call is going to do the right thing. And you have the correct base case. So again, you have to print the thing that like is at your node that you haven't yet considered that's not part of the smaller list. So where does the 1 get printed? Is it before the recursive call or after the recursive call this time?
After.
It's going to be after. Yeah, so if this is the recursive call, it's doing that printing. The 1 now needs to happen later because it's in reverse order. That's different. It's the opposite of this one, right? Where you had to print your 1 first because it needs to occur in actual order. If we want in reverse order, it's got to happen last. I hope makes a little bit of sense. So that's your recursive case. So the recursive call on your smaller list prints the smaller list in reverse order. You do that first. We know that answer now. And again, you could have the same base case. You'd be like, all right, when the list is empty, that's always going to be your base case. Usually. You'd be like, how do I print all the elements of an empty list in reverse order? Same as you did for normal order. There's nothing to do. Do nothing at all. So that's going to be your recursive print in reverse order. And it's pretty much going to be the same code, just these 2 lines have switched, isn't it? So if you mess it up, you got reversal. Which kind of makes sense now that we've talked about it, I hope. So this is like, we'll call this print in reverse order, I guess. Let's call it print in reverse. Just remember to call yourself properly if it's not called print in order and print in reverse. And yeah, the idea is recursively print the smaller list in reverse first, and then print the first node's data. So the only thing that's changed, like these names don't matter. This could have been called F, right? This could have been called F. The only difference besides the name of these 2 functions, these 2 recursive functions, is the order of the recursive case. That's all that's different. It's crazy. So you get reversal just if you swap those lines. And I hope you see that. Like that's how we reasoned about that. It has to happen first and this happens second. Like that's how we get reversal. We just assume it works. It will be happy. Okay? So yeah, let's do a print in reverse now. Call. Let's have like a little line to separate things. We'll do print in reverse. The entire list, so it's starting at the first node. Pass the whole thing that way. And look at us, we got the 3, 2, 1. It's working for the same reason. I highly encourage you to draw what the stack looks like here and how it's thinking about things. This is going to be slightly different. Any questions about this code and why it's correctly going to give us 3, 2, 1? So yeah, just believe in the magic of recursion. It's going to work on the smaller call because it will make its way down to the base case, build that answer up as it needs to. Okay, so that's how that works. Recursive print in order and in reverse order. I've got a couple more. Or no, just one. Just one more. Let's do a recursive search. Okay? Let's say I would like to find something in the list. There's no concept of an index. I guess you could think about it that way if you wanted to, but let's just give back a Boolean. Let's give back true if we find the value that we're looking for in our list, or false otherwise. So we're going to have an extra parameter. We're going to be like search through the list starting at n for some value. I don't know. The value can be like 1 or 2. What do I want to start with? Well, let's do 1. I think that's fine. So again, if you want to search for something in your list, you are going to, and you want to do it recursively, again, you're going to break down the list into your first node and the rest of the list. You get to get, it's guaranteed that the recursion, right, if you ask it to search that smaller list for that same value, right, because you're always going to be looking for the same value, the goal is to return true or false if you found it or not, all right? So you're always going to be making your recursive call and be like, hey, I'd like to search the smaller list starting at n arrow next for the same value, and you're guaranteed to get back true. Like you get, just assume it does the right thing. You get back true if it's in there and false if it's not. So you're going to get back for this particular call, for this value, looking for 1. You get to assume that you're getting back false. It didn't find it. As long as you build up the final answer correctly, that really will work out. The recursive call really will work out. The last thing that you need to check, right? The recursive call is going to search in the small list, give back true or false if it's there or not. The last thing that you need to check is the node you have not yet considered. Just your first node, because that's actually where the 1 was, right? So as long as you guarantee, like recursion's guaranteed to check the smaller thing, as long as you check the one thing that's not there, return true or false based on that, you're kind of good, right? So if it was here, if it returned true here, like if there was a 1 here, like, all right, just return true. It found it somewhere. You're happy. But if that was false, then it might have been here as well. You got to check there too. Return true if you find it there. Otherwise, then you give up. Like it really was false. It wasn't there at all. Does that make sense? That's kind of what needs to happen there. And so it depends like what the val was. The val could have been 2. And so like you do the recursive call, it's like, oh yeah, it finds it. It returns back true. So you don't even need to check your first element anymore. It's like, all right, it was there. So sometimes it's there, sometimes it's not. As long as you remember to check the other thing, because it might have been there, you're given back the right answer. True if you found it somewhere, false if you didn't find it anywhere. And then think about the base case. What's the base case going to be? Again, it's the empty list. You're searching through a value in the empty list. Will it ever be there? No, so immediately you can return false, saying I didn't find it for your empty list case. I hope you kind of see how that's all coming together. So here, let's pretend I've got all these things. Let's call it for every element, just to prove it's going to work always. So I'll call it search. Search the whole list, starting at first, for the 1 element. There will be a 1, so that'll be true, true, true. There's a 3. It goes 1, 2, 3. And if we search for 4, it'll finally be false. So like that's my search function. That's what I want to do. How do I say this? It's going to be called search. It's going to take a list, node start n where it begins. It's going to take a value where it wants to search for, and it's going to return back a bool this time. Did it find it or not? True or false? So its job is to search the list starting from node n for the value called val. Okay, so again, base case, recursive case. If we're in the base case, n is the null pointer. We have no list at all to look through. So we're searching through the empty list for a value. It will never be there. Return false. Immediately, I did not find it. Otherwise, if I actually have some values in my list, actual nodes, recursive case, non-empty list, well, either, right, the value I'm looking for is in the smaller list. It's here somewhere, or it's in the node that is not part of the smaller list, my first node. It's one or the other. Could be in both if it's duplicated. So either val is in the smaller list or it's in the first node. As long as I've checked all those places somehow, I will be giving back the correct answer. So let's make some silly long booleans. Like I'm getting back a bool when I search the smaller list. Like, right, if I search the smaller list, that's search the list starting at n arrow next for that same value, I'm getting back true or false, and I'm guaranteed to know if that was in the smaller list. Like that's what recursion gives to me. It's like that's bool. I'll call this, was it in the rest of the list? Very long variable name. All right. But that's what I'm getting back, right? That's what I'm guaranteed to get. As long as I do everything else right, the recursion will check that smaller list for the thing. I'm getting back true if it was there, false if it wasn't. All right. And then the only other thing I need to check is the thing that the recursion did not check, the bigger, slightly bigger list, bless you, which is the one node. All right. So there's that one. So like that's bool, was it in the first node? That's like, hey, is n's data equal to the value? True or false? And then our final answer was like, either it was here or it was here. If it's anywhere, I want to give back true. So return whether was it in the rest of the list or was it in the first node, true or false. If it was anywhere, it'll give back true. If it wasn't in either of the places, it'll give back false. Okay? Like that's my answer. Does that make sense? Like, was it there or not? You get to just, you can stop thinking. You can be a little lazy. Like that's what recursion gives to you. It's like as long you get to assume it was a smaller call, it's going to do the right thing as long as you build the answer back up properly. It will make its way down to the base case. Do it right. So I see true, 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 false, which is exactly what I wanted to see. Because there is a 1, 2, 3, but not a 4. Okay? So that's your search algorithm. Are there any questions about it? There's a way to do it this way, like give back an index, even though you don't really think of it that way. Like index 0 if you found it in the first element, index 1 if you found it in the second element. Like there's a way to play that game. Highly encourage you to try it. I can help you with it. But you'll have to keep track of some other things potentially. That's a little weirder, but kind of cool at the same time. But it will work. So that's recursive search. Yeah, I think that is most of what I wanted to say. Yeah, I just want you guys to discuss now that I've talked about a bunch of recursive algorithms. You don't even have to write this down. I'm not going to look on the written nice page, but I'd like you guys to please have a discussion to think about, like, let's say we've got a linked list and we would like to reverse it. All right, there is a way to recursively reverse a linked list. Yeah, and so like here's the smaller list for 1, 2, 3. Your job is to maybe give back a new list. Let's say like a new list. Dun, dun, dun. That is, you can make copies of things, that's fine. That is 3, 2, 1 instead of 1, 2, 3. I claim that there's a way to do that recursively. You don't have to don't think about the code, think about pseudocode. Think about like what your book's saying, like words, the recipe. How would you do that? If you had to break it down this way, there's your recursive call. Think about what that gave you back, and then how you'd attach the extra thing, right? Because the thing that hasn't yet been considered, you have to worry about. So take a few minutes to just discuss, like, all right, recursively, how would I think about reversing a linked list? Like, here's my whole list. I can make a recursive call. Think about what that gives you back in terms of this problem. If your job is to give back this kind of list, just in English, how would you do it? All right? Have that discussion, please. Take a few minutes. You don't have to write it down. The base, yeah, think about what is the base case? Is it still the empty list? Sometimes it doesn't have to be. It could be like the size one list. I think empty list is probably fine. All right, our voices are starting to die down. It sounds. I don't need you to type this up anywhere, but like, let's think about it. Like, if you make the recursive call, what are you getting back on the 2-3? Like, it's returning to you a list, right? A reverse list. So you're getting back a pointer to the start of it because that's how lists are represented, right? You're going to give back a pointer to the start of that list with the 3 and the 2 in it, right? And it will be a correct list, so it'll look like that with a null pointer after 2. What's your job then after that? Is to add in that 1, right? So you're going to have to essentially iterate to get to the end of that list and add in that last node, that 1 node, make a brand new node with the 1 in it now. It's kind of like you're calling pushback, or you're like implementing it yourself as part of the recursion. Like you make a new node 1, do that. Does that kind of make sense for the recursive case? Like if you could code that, that's what would happen. Something like that. We don't have to code it. So that's the recursive case. The base case then could be you're given null as I have this empty list. I'd like you to reverse it for me, please. What do you give back? How do you reverse an empty list? The list that is empty is the same forwards and backwards, right? Just give back null again. There you go. I've reversed it for you. So that's pretty much how that's going to look. Okay? So something like that. Is that what we came up with? Are there any other ideas? It's like you're getting back a list, and you have to think about how you're getting it back, right? How do you return a list? How do you represent a list? It's by a pointer to where it begins. So you have to think about that. It's fun to think about. All right. Yeah. Any questions about this question? It's just a cool one to ponder. I think highly encourage you to try it. I can help you with it. Great way to study, practice. Yeah, if you're good. I had another question, but I think we're running out of time. So, like, I want you to think about this yourself after class if you can. Like, come up with an idea where, like, we know about arrays and linked lists and how they compare. Like, come up with an idea of, like, where you would actually, like, I want to use an array right now. I need that. A linked list would make things horrible. Because you know about running time complexity of all this stuff now. And then also do the same thing, but like, I really could use a linked list for this problem idea versus an array. An array would make things so much slower. So there's totally plenty of options there, and I'd highly encourage you to think about that because like that's why we're learning this stuff. So yeah, if we're good, I think that's most of what I wanted to say about lists. Are there any questions about any of the stuff that we talked about today before I just teach you something technical that's useful for your labs? All right. So if you have never seen this before, I want to give you a short little lesson on something called GDB. All right, it's going to be very useful for your lab. GDB is short for the GNU debugger. So this is going to be a wonderful piece of software that you want to use. It's lovely. It was made by the same people who made G++. G++ stands for the GNU C++ compiler. So the GNU people, with a hard G, they've made some nice things for us. So let me teach you how to use, it's a program on the terminal called GDB. You can run your own program inside of it, and it will tell you where things go wrong. And you're going to need that, especially for this lab, for the future labs that involve a lot of pointers. So you could have probably used it in the vectors lab, but now you had to struggle so that you can see the light here. All right, so let me make a sample program with some bad stuff and teach you. So GDB example.cpp. So let's see, let me make this, what do I do in my CSCI 40? Let's make a function called that's going to do something bad. Int x equals 42, int star I equals null, and oh no, cout star I. So you see the problem here, of course. And I'll call from me. But what if you didn't? You're going to have subtle stuff, especially in your labs, where it's not going to be as easy as this to track down. So here's how you can use this magical thing called GDB. It's going to save your life, I promise. It's something to come back to this slide forever and ever. All right. To use GDB, instead of compiling normally GDB example -o GDB example, that's not good enough for GDB. GDB wants some extra stuff, so you got to say G++ -G, please. That's the new thing. You add a -G as you're compiling. That is what it wants. And that will add some extra information as it's compiling in terms of like the code itself and the line numbers, and that's going to be super duper helpful. So that's why we do that. So add some extra debugging information to the executable file. So you compile it like this with a -G flag. It's called a flag. It's like it's on a little stick. And then it's still a program that you can run as normal. Like you could run it as normal, that's fine. We know it's going to segfault. It would have run just the same, but the -g gave it some extra information so that you could have also run it in GDB. All right, and that's where we're going to go here. So the way that you run your program in GDB, like you notice that something went wrong, like a runtime error, you just pretend to run it and then you tack the GDB command at the start. That's all you got to say. Like GDB, please run that program. That's how I want you to think about it. So that's what you do. You say that and you hit enter, and that will start running that program in GDB. Or it will get it ready at least. And so my terminal is very small right now, or very zoomed in, so it's like asking me to press enter. It's like showing me copyright information. But eventually, you get to the GDB little command prompt. So we're inside of GDB right now, and it's ready to run our program. Okay, so like we have a GDB terminal now. And what you do, here's the ones that I want to teach you today. You say R to have it start running your program. So it hasn't actually run it yet. It's got it ready and loaded. You say R for run. You hit enter in GDB land, and it runs your program. And do you see how it's already amazing? It says, oh, segfault. You know what? That happened on line 7 of this particular file in this particular function. Oh, by the way, here's that line just output for you for your convenience.
Wow.
Is that not the best thing ever? That's going to save our lives and so much time as we run into these problems, because of course we're going to, as we're starting to learn how to deal with pointers in a fancy way. That's lovely. That's so, so nice already. If you want to see, because maybe there's a bunch of different ways you could have come up to this function, like there's a bunch of different ways in your program that it could have been called, you can say BT, it's short for backtrace, to show where you are in the stack. Like, what does the stack look like? What are the chain of calls that got us here? So here's a picture of the stack in text form. It's like main on line 11 called and we were on line 7. So it's like that was the call. There were different calls to with different parameters maybe. Cool, right? That's amazing. And like, okay, that was the line. So that tells you how you got there. Very, very useful. And we are by default, we're always in the upper, the tallest stack frame, the uppermost stack frame. We're in right now, looking at its memory. If you want to move throughout the stack, you can say up and down to go throughout the stack. Like, okay, we're sitting in right now. You can say go up out into the call to main to like look at the memory around main. You can say down again to get back to where we were in like that's how it looks. We can move around the stack to see memory values, because not only do we know the line numbers, GDB, even though the program has crashed, it's remembered all the values of everything. It's the greatest thing ever. So like you can start printing things. You can say, depending on what stack frame you're in, you have different things alive. You can move around as needed, but you can say print space, the name of a variable. You can even call functions sometimes. So I can say print space, like I'm in right now. I can say like, okay, why was this the problem? Let me inspect my variables and print space x. It's like, oh, x was 42. Oh, that doesn't seem like the problem. Print I. Oh, that's the number 0. That's the address 0. I think I see the problem now. See that? That's great. You could even try to dereference it. Print star I. That's what we were trying to do in the cout line. Oh, okay, yeah, I remember now. That's the null address. I can't go there. There's nothing there. That caused the segfault. Do you see how that's going to make your life so much easier? It is the best thing. The best. There's even cooler things you can do with GDB, and I highly encourage you to like look up tutorials, because the more you learn, the easier it becomes to do all the labs in this class. All right. So yeah, that's more or less what I wanted to show you. That's enough for now. To get out of GDB, you can do Control-D, or you can just say quit. There's a quit command. And it's like, hey, I'm running your program right now. Are you cool with me stopping that? You say why? Yes. And it gets you back to your terminal. All right. So that is GDB in a nutshell. Just remember the -G. I will give you make files that default and give you the -G for you, so that you're golden there. But like that's how you do it. R for run, BT, show the stack, print variables, move up and down the stack as you need to see stuff, and quit to quit. Any questions about that? I hope you see that it's useful, and I hope you come back here and remember it. So yeah, there's that. And the last thing for the day is, let's talk about your next lab. So you might as well, you're ready for it now. I'll give it to you. You have plenty of time. That's going to be due after the midterm. So let's see here. Dun, dun, dun. Here we go. This will be fun. All right. First things first. Now that you guys like know enough C++. You've remembered things. I'm happy with you guys potentially working in pairs on your future lab assignments. So starting from this lab, you can work in pairs, and I think I'll have that true for the rest of the semester. So what I want you to do, if you choose to work in pairs, groups of 2 only, no more than 2, you must still please submit separately to the auto grader. It's easier for me to give you a grade that way. It's already baked in. But I also want you to include a comment in your code somewhere at the top of at least one of the files saying who you worked with. At least one of the files that you're turning in, right? That saying who you worked with, so that I can see that and not like get you in trouble. And yeah, I can help you transfer code between yourselves if you're having any issues with that. There's plenty of ways. You can post on Discord if you want to find a partner. I can start a list of people who would like partners potentially. If you want to be added to that list, we can do that. But yeah, that's the first thing. And yeah, the next stuff, like this is a linked lists lab, but also a pointers lab. So I want you to get practice with like GDB and stuff like that. So let's look at the files. We've got we'll start a code 41. What was this lab? What? Lab 4. Here are the files as you get them. There's a bunch of them. There's a make file. And there is -G all over the place. So it's always going to work in GDB if you need it to. And yeah, so the first step of this is I want you to just practice GDB some more. I really think that would save your life if you just kept trying that. So I've made a little segfault.cpp file that you're not going to turn in, but I think you should try it. All right. So here's some things that have a bunch of errors. Use GDB to notice the errors and fix the program and get on to the next error. Notice the error again, the next error with GDB, fix the program. I think that would be a great exercise for you. Okay, so I've given this to you not to turn in, but to practice. Okay, yeah. And you can use the make file to say it like this is make segfault, but you could also have compiled it with G++-G. Right, and that's what it's going to do for you. And yeah, to load it into GDB, like you pretend to run it, and then you tack the GDB at the start. Okay, and then you follow all the rules, all this stuff from here to make it happen. Right, so that's the first part of the lab. You're not going to turn that in. And then once you're practiced with that, you can implement a linked list class. So it's called list with a capital L, like I drew, I guess. And that's all in list.cpp. So you got a header file, list.h, and an implementation file, list.cpp. And of course, we got nodes. And so a list is, it's got the big 3. It's got first and last. Give me the first and last pointers so I can iterate maybe. There's push front, push back, pop front, pop back. Give me the size, first and last. Do not be alarmed by the piece of data that's inside our list. The list could hold anything. The list could hold ints and strings and bools, whatever. I'm choosing to have it hold something called a point2D, which is a 2-dimensional idea of a point. This is what a point2D is. It has an x and a y member variable. Like it's keeping track of a 2D coordinate for like a game, potentially. And so we'll get into that. You don't have to worry about it. Nothing changes. The algorithm does not change at all for insertion and stuff like that. It's just like you're given some data, put that data in your node, whatever type it was. It doesn't have to be an int. It's a point2D for you, okay? That's what's happening. So that's what nodes are. They got data as not an int, but a point2D. And that's what you're getting when you're pushing front and pushing back. That's your piece of data. But that doesn't matter to you. That could have been anything, okay? That could have been anything, and we could make that better once we learn about templates. Let's see. So that's that. So like these are the things you're implementing. Your member variables are first and last, just like we talked about. So everything I drew, you can implement. Nothing has changed there. And then you're doing it all in this file. All right. So I've given you some comments. I've given you some starting points, but it's more or less you are going to look at my diagrams and read the book and implement what needs to be implemented here. All right. So constructor should make the list start out empty. Get first and get last. They're just getters so that you can move around as the user. They're public things. Public windows into our data, but they're const so that the user can't change things. You just look. Push front, push back. You know where to go for those, right? Pop front, pop back. So I've given you some helpful comments. Look into those. Size. We've made a trade-off here for size, because size, you could have done a member variable for size. You could have been like, every time you push, you add 1. Every time you pop, you subtract 1. But for us, we're just going to have it be like go and iterate. So we've traded space for time. It's probably a bad trade-off, but it's a good thing to implement. All right, then we've got the big 3. So you got the destructor, make sure to delete every node in the list. You got the copy assignment. This line just gets it to compile, delete that line, just like every other lab with a copy assignment. It's like this is completely incorrect, has nothing to do with the right answer. So yeah, you know what you should always be returning in a copy assignment. And then copy constructor, we talked about that too. So those are all the things that you'll be implementing for this particular kind of list. It should work for ints, works for point2ds, not a big deal. All right, there's no real difference. And yeah, once you get that working, I've made a linked list tests file, and that you can get with the make file. So make linked list tests. It will bring in your list library and get things working. All right. So I made a bunch of tests here. The one thing about these tests are none of them will pass unless size works. At the very least, all of these tests are going to check the size of the list that it's building up. So if size does not work, everything's gonna fail. So just keep that in mind. It's not the hardest one to implement though, but get that one first maybe. So this is like push front. It's adding a 2-dimensional thing to a 2D point to the list. It's making sure that, oh yeah, after you added it, like initially the size was 0, then we added one thing, the size should be 1 now, and the X and Y data of the thing that we just added is like the first thing was 2, something like that. You add another thing, the size better be 2 now. So like that's kind of how it's thinking. Pushback is similar. Pop front, just like making sure the size is going down properly. The first and last things are what they should be, stuff like that. And I can help you understand these tests if you need to. Like copy constructor test, copy assignment test, making sure that you didn't do weird things with self-assignment. Gotta watch out for that. So yeah, those are my tests, and you do not need to write any of your own this time. Okay? Any questions about what you're doing? Because that's going to be the bulk of your lab. You got this list.cpp file. Implement a linked list class, please. Implement a list ADT using a linked list as the underlying data structure. That's what I should have said. Any questions about that? Because once you get that working, I've made a game for you. You know the game Snake, where you like move around and you, like eat the little things and the snake gets longer? Go look that up. But I've made this for you. Do not look at the code. It's disgusting. Unless you really want to. I don't even want to explain it, but like it needs all of these libraries. And I have made, because all you need, if you think about the game Snake, the thing's moving around, right? All you need is to remember where all the pieces of the snake's body are, and those are 2-dimensional coordinates. That's what's in our linked list. So I've made this for you. You don't have to do it yourself, but all it's done is it has made, at the underlying like one of its member variables of the snake class for this game that I made is the body of the snake. So this will be very, very satisfying. Once you get all the tests to pass, you should be able to play this game, and let me show it to you. So yeah, like that's a great use case of a linked list. Like you couldn't have used something else very easily for that. So let me show that to you. Oh shoot, I don't have it. Give me a second. This is worth it. I need to go to GitHub, this class. Am I signed in is the question. I am not, so give me another second. Yes, and it's going to make me do... Ooh, is there a passkey? I don't think there is. No, whatever. Do I have this? Oh no, I don't want to deal with that. Or do I? More options. I have that one. Yeah. Why it needs to be so complicated, I don't know. I have an AutoGraders repository that you don't get to see. No, it's all right, but I'm going to bring it onto my own machine right here. This is a new laptop, and I didn't have it. So, boop. That's where I have solutions. I think it's just make snake probably, right? Let me see here. Make snake. So here we got AutoGraders 41. Is it 4? Solution. Yeah, make snake. And here it's not the most complete snake game, but it does work. Here's what it looks like. You can use the arrow keys to move around. It's a little choppy because it's like,
Yeah.
it's a terminal. But look at it, got one longer, and it's saving where it lives, like the size of that snake, in coordinate form as a linked list. Whee! Look at it go. You're not really supposed to go over the edges, but like I have not programmed the other way. Like it's getting longer. It's remembering where it lives, and that is a linked list. Deep down, it's saving the coordinates of where the body of the snake is, and it's advancing it each time. Like it's kind of like pushing and popping, pushing to the front, popping to the end every time it's moving. If you want to think about it that way. So that's kind of cool. You can press Q, I think, to quit out of that and get back to normal land. But that is, oh goodness, cool. That's what you get to enjoy once you get things working. So that's kind of cool. And I think that's all that I wanted to show you. So the GDP practice was just for you. The snake was just to enjoy the fruits of your labor. All you're turning in is list.cpp. That's what you're working on for this lab. All right, so you got plenty of time to do it. We do after the midterm, but I think it would be a great way to practice pointer stuff if you get started early. Yeah, and so that is your lab 4, and I think that's all that I wanted to say about it. Are there any questions about this or anything else? All right, I've done enough talking today.